On the left, we see the transfer function for a low-pass filter. That's the cutoff frequency divided by S plus the cutoff frequency. On the right, we see the transfer function for a integrator, an integrator that just integrates without any gain. Okay. Now, last class we said that an integrator can be approximated by a low-pass filter. For what frequencies? For what frequencies can an integrator be approximated by a low-pass filter?
Can you repeat it again? Sorry.
Well, what frequencies
from a range of 300 to 3,300 hertz?
Young man, first of all, that was just one example. I'm talking about in general. Why didn't you learn the general rule? Why did you learn the specific rule for that particular and for that particular example? Why didn't you learn the rule that fits for all? Look in your notes, please, and tell me when does a...
The only other thing in my notes that I was talking about frequency was F had to be greater or equal to 10 times the cutoff frequency, or the frequency had to been, or the cutoff frequency had to been less or equal to F divided by 10.
F divided by 10, what F?
That would be meaning the frequency.
That'd be what?
That would be the frequency.
The frequency of what? Please repeat to me what you just said.
Yes, sir. So it was, at least what I wrote down, it was 3 instances. So the first instance was if F was greater or equal to 10 FC.
All right, so you got F greater than 10 FC. What is F and what is FC? What's the point in having an equation if you don't know what the terms are related to?
I would assume the F would be meaning the frequency we at, or what we're using, and then FC is our cutoff frequency.
FC is the cutoff frequency. FC is the cutoff frequency, and F is the frequency of the sine wave that you're dealing with. All right. So let's show that mathematically. So we are not going to get this. That's a true integrator. However, we can get one of S tau is one of omega C of S. We can approximate this. This is what we're approximating. We need to make this look like this. This is what we want. This is what we have. How do we make this look like that? We want the cut. How do we achieve that?
We have to find somebody to move the omega C.
From the bottom.
Yes, sir.
All right. We're making progress. We can't remove omega C. What can we do to make this term a lot bigger than that term? What can we do? Because if this term is a lot bigger than that term, then this bottom is approximately this bottom. What do we do to make this term approximately this term?
So you divide the omega C by itself, no? On the denominator.
How does that help? We simply make omega a lot bigger than omega C. We make omega a lot bigger than omega C. Then this term is a lot bigger than this term, and this term is insignificant. We've done this many times in this course.
Would we use a log function?
What do we use a log function? What do we use a log function for? We simply make omega. What is omega? Tell me what is omega?
2 pi f.
Omega is the frequency of the sine wave.
Omega is the frequency of the sine wave. The lowest frequency or the highest frequency?
The lowest frequency.
The lowest frequency. So really, we want omega L, the lowest frequency in the waveform. The lowest frequency in the waveform. Okay. What do we mean by a lot greater than? What do we mean by that?
At least 10 times.
So omega L must be greater than or equal to 10 omega C. Or another way of saying the same thing is omega C. Okay. Must be less than 10 times omega, 10 omega C, omega L. So omega C, the cutoff frequency, must be less than or equal to what? The lowest frequency divided by 10. This is the equation I gave you last class. That's the equation I gave you last class. Now you know where it came from. Except I said SC is less than or equal to what? FL over 10. This is what I gave you. But of course, this is 2 pi f, and this is 2 pi f. Okay, so we divide both sides of this by 2 pi, and we get this. Okay. So now, if this term here is at least 10 times bigger than this term here, then this entire term is omega C over j omega. All right. Okay. So what's omega C equal to? For low pass, what's omega C equal to? For a low pass filter, what is omega C equal to?
That's negative 3 dB.
A frequency equals dB? Really? Rise per second equals dB? That makes sense. That makes sense to you? I can't believe this. I can't believe this. Y'all don't retain anything. I don't know why I bother teaching. What's the cutoff frequency of that?
That's 1 over 2 pi RC.
So how come you know it when I draw it, but you don't know it if I don't draw it? So omega C is 1 over RC. Omega C is 1 over RC times 1 over J omega. So what did I just show you? This is the integrator. That's a true integrator. That's a transfer function true integrator. And a low pass filter will give you this gain, 1 over RC, times a true integrator. Okay. If this is true. That's what I just gave you. I'm going to please snip the page, Agent. This is what I told you last class, and now I just showed it to you mathematically. Okay? So omega c over s plus omega c, first order low pass filter is approximately, and this of course is 1 over RC over S plus 1 over RC. And this is approximately 1 over RC, 1 over S. If FC is less than or equal to FL over 10. Okay. So first of all, low pass filter looks like a true integrator. That's a true integrator multiplied by gain. Just a constant. That's what I showed you last class, and now I justified it mathematically. So let's see this in action. Let's see this in action by PSpice. All right. Here's a PSpice simulation. Here's a low pass filter. What's the cutoff frequency of this low pass filter? What's the cutoff frequency of this low pass filter?
You could say 100 hertz.
100 hertz. Yes, 100 hertz. And why did I make the cutoff frequency of this low pass filter 100 hertz?
Because it's 10 times less. The same formula we had on the previous page.
Yes.
Should be the lowest frequency divided by 10.
And so what are we saying the lowest frequency is?
The lowest frequency is 100.
No, the lowest frequency is not 100.
The cutoff frequency is 100.
And so what do we say? The lowest frequency is how much?
You know right now. The lowest frequency should be 10.
Really?
Oh, I don't know right now.
So 100 is less than or equal to 10 divided by 10.
So you're trying to say the lowest frequency is 1,000?
I'm not trying to say that. I am asking you to say that.
On the formula, it should be 1,000.
Yes, that's the only thing that would justify me using a cutoff frequency of 100. Okay. Now, what kind of waveform am I applying to this low pass filter? What kind of waveform am I applying to the? What's the input to this low pass filter?
Square wave.
A square wave. A square wave. And how am I creating my square wave? All right, let's deal with square wave. That's V square. That's V square. You see it there. V square is the input. It's a square wave. We'll talk about in a minute about how I generated it in PSpice, the square wave and PSpice. There are many ways to do this. I'm only showing you one way. What frequencies are present in my square wave? This is now a 320 question. What frequencies are present in my square wave? Wow. You know, some universities have an X exam. I don't know if I told you this before. It doesn't matter what grade you get in each course. You get an A in a course, and if you can't pass the X exam, you won't graduate. The X exam is kind of exam of all the courses you've taken for that program, for the major program, for the major in that program. And if you don't retain the knowledge to be able to pass the X exam, then you don't graduate. If we had that policy at UB, all of you would be in trouble. What's the point in learning something if you don't retain it? I would advise you go back and look at Fourier series. A square wave has odd harmonics. The fundamental is 1,000. Therefore, you'll have 3,000, 5,000, 7,000, 9,000, 11,000, 13,000, all the way up to infinity. Let me show you that. Let me take this one off for a second. This is getting in the way. All right. How do I find the frequencies? What do I do to find the frequencies? I showed you this also. What do I do to find the frequencies present in this waveform?
When you have the brass, I think that FFT button or something like that.
FFT, exactly, FFT. Okay. And what do you see? What frequency is present? Well, there's my 1,000 there. There's my 3,000. There's my 5,000, 7,000, 9,000, 10,000 is not there. 11,000 is there. We could even make this better by going out to maybe 21. See, you can see it better now. You can see the frequencies present. And not only can you see the frequencies present, you can tell how much they are. So the amplitude of 1,000, let's get the peak. It keeps climbing. Okay, about there. That's basically 1K. See the x-axis is 1K. And if you remember how to do Fourier series, you would know the theoretical value for that amplitude. The theoretical value would be 4 over pi, and 4 over pi is 1.273. Okay, and then the third harmonic be a third of that, and the fifth harmonic be a fifth of that, and the seventh harmonic be a seventh of that. We did all this in 320. So indeed, the minimum frequency is 1,000 hertz. The minimum frequency is 1,000 hertz. Therefore, what should my cutoff frequency be? My cutoff frequency should be less than 100 hertz. All right. Any questions about that? Okay. So there's, what am I expecting my output to be? There's my input. My input is a square wave. What am I expecting my output to be?
A triangular wave.
How do I compute? How do I measure what my output should be? How do I measure the theoretical? What's my theoretical output? Yeah, I gave it to you. My theoretical output is 1 over RC times my theoretical integration. Integrate that square wave and multiply by 1 over RC. That's what I'm expecting as my output. And let's see if that's true. So let me Let me get my output. There's my output. Okay. Let me simulate this. And there's my green. The green is my triangular wave, like Mr. Johnson said. There's my triangular wave. But it's the triangular wave it's my simulated. Now let me add my simulated integration. I'm integrating the input. I'm integrating the square wave. Let me do that. So how do I integrate in PSpice? I go for S. S of what? F of the square wave. Okay. And what has happened? I get the blue, but the blue don't look like the green. The blue should look like green. Why doesn't the blue look like the green?
Do you have to adjust your final time?
No. Why do I have to adjust my final time?
I was just thinking about the last PSpice assignment I had. That's when.
Yes, but you have to think about the present assignment I'm giving you right now. You have to think about the theory I've given you already. What did I just finish telling you? What did I just finish telling you the output should be, theoretically? Did I say the output should be the integral of the input? See it right here on this page? What should the output be? That's the integral, and that's the gain. We didn't multiply by the gain. This is the theoretical output. This is the theoretical integral, but that's not what this circuit does. This circuit gives us the theoretical integration multiplied by a gain. What's the gain? 1 over RC. That's the gain. So we did not multiply by 1 over RC. And 1 over RC is going to be 628. 628.1, I think. Where did I get that from? Okay. Well, you know what RC is. We just take reciprocal of it. And there now you have it. Now you have the blue lies on top of the green, telling you what? They're very, very close together. And of course, I got too many cycles on this. But that's because of something I had earlier. Okay. If we'd stopped at 5 milliseconds, that would have been fine. So there are too many cycles on this. Does everybody understand what I'm saying here? I am saying the output of the circuit is not the integral of the input. I am saying the output of the circuit is the integral of the input times a gain. What gain? 1 over RC. Why? Because that's what the transfer function says it's going to be. So this is not just this circuit, this low pass filter. It's not just giving us the integral of the input. It's giving us the integral of the input times gain. And what's that gain? 1 over RC. Any questions about that?
Just to be sure, you say the output is the integral of the input multiplied by the gain.
Yes. See there? VL phasor equals what? The transfer function times VI phasor. Okay? VL phasor equals H, 1 over RC times 1 over S times VI. What's VI over S? That's the integral. That's the integral. In the time domain, that's the integral. What is this? This is just gain. But this is only true if that's true. Otherwise, VL phasor is 1 over RC times S plus 1 over RC times VI. This is true. This isn't true. That this is approximately this. This whole thing. If this is true. Any questions about this? All right. Now, let's get back. How am I generating this square wave? I'm generating this square wave from a sine wave. You see that? This is a sine wave. Actually, it's a cosine wave. I'm switching. Everybody got a snip or two? This is my sine wave. All right. That's the period. So here VI is VM sine 2 pi over the period T. Okay. That's the equation. Or we could do this. And this VI2 is VM cosine. This is 90 degrees ahead. Cosine 2 pi over T.
So Dr. Cartwright,
Yes,
so that's why on the PSpice you shifted 90 degrees.
exactly. Because this here is VM sine 2 pi over T plus 90 degrees. That's exactly right. And PSpice refers everything to sine. Now, what mathematical function do I do to this to change that into this? To change that into this? I only have one answer? Really? Come on, folks. If I don't get more answers, I'm going to turn this into a test. Miss Buchan, please don't tell them, because I need to know if they're understanding. Mr. Johnson, please read. What page is that? Please read page 5.
Yes, sir.
It's on page 5. It's summarized on page 5, but it's also on page 4. I'm still waiting for answers. If I don't get answers the next minute, I'm going to make this a test. Mr. Stewart, please read page 5. Miss Adley, that's not an answer. I need something that says Hertz.
Oh
I
no,
need a new.
I was looking at page 5 and I was thinking about something else. My bad.
Yeah, you were thinking nonsense. That's what you're thinking. I need a numerical answer. I'm asking for the cutoff frequency. Cutoff frequency of the high pass filter. I need one more person to respond. One more person. Or any of the three who got it wrong. Let me see a second guess.
It has to be in hertz, right?
No, it could be in rats per second. Since I didn't specify. All right, pay attention, please. It's page 5. It's page 5. Okay. Here's the high pass filter. When is the high pass filter approximate differentiator with gain? When is that true? See it right here? When omega C, the cutoff frequency, when the cutoff frequency is greater than what? 10 times the highest frequency in the signal. What is the highest frequency in the signal?
It's
3,300 hertz.
3,300 hertz. That's FH. That's not that's not omega H. So we need omega C or FC greater than 10 times FH. FC greater than or equal to 10 times 3,300. 3,300. What about that? I give you the answer in black and white, and you still can't. Well, you better learn how to do it for the take-home test. Any questions about this problem, this example? Okay. Let me know.
Dr. Cartwright, back to that piece spice. I have one question.
Yes?
The box. Yeah, the box. Well, hold on, pull it up. I can show you what I talking about. The piece spice schematic.
Yes?
Yeah, how you got that? Did you just put a box there and just put in the figures in, or you?
Yeah, man, were you not paying attention when I showed you how I got that? I told the
No,
class how I got that.
well, that went over my head, Mossy, because I still didn't understand that.
You don't understand because you weren't paying attention.
No, I was paying attention. That's why I could have remembered to come back to this. 'Cause I was looking at that for the longest, but I still didn't catch on what you was trying to say.
What's the pod called that I use? You see, you all do your own damn thing when I'm explaining stuff, and then you expect me to explain it again to you individually. That's not how this works. You pay attention when I'm explaining. I said you use this part number here, ABM1. That's what I said. Okay. And then you put the function in that you want to create, and then we want to create the sign of the input. Whereas this one right here creates the input times 1/10. You double click on that. And then you can write in the function you want. What don't you understand about that?
And then we have to create the function in the theoretical, right?
You have to create the function you want. How is the output related to the input? This is giving you the output. How is it related to the input? This is V percentage N. That's telling you the input signal, the input voltage.
All right. Got it. Thanks.
Okay. Um, everybody got page 6? Okay.
So, Carter, the next thing, when I do this assignment, I can try get it due as early as possible. Would you look at my mistakes if I have any mistakes and
Well,
tell
I'm
me how
not,
to correct it?
yo man, I'm not gonna grade your paper before I grade your paper.
No man.
What professor does that? What professor looks at your homework, tell you what you do wrong, so you correct it before you hand it in?
Nothing wrong with that, man. We striving for excellence, man.
You do it,
Right.
yeah, but that'll be me doing it. That'll all be you doing it. You can strive for excellence. You can strive for excellence if you want, but I'm not gonna do your homework for you.
No man, you only guiding us through it, man.
No, if I'm telling you what you're doing wrong, that is me doing your homework for you. Nobody does that.
So you supposed to just get it wrong if you don't understand?
Yes. Or if you think it was wrong, then you ask
Yeah,
questions.
that's what I'm trying to say. I ask them when I do it. I ask questions.
You want me to tell you whether that was right or wrong. I'm not going to tell you if it's right or wrong.
So how are we supposed to pass, man? Or how are you supposed to pass?
Yo, man, what professor does this?
All right, boss. That's straight, man. Dot carries.
Nobody does that in high school. Nobody does that in university. You do your homework on your own, or you get help from your colleagues, your classmates. I will answer a question, but I will not answer whether or not your question is right or wrong. And the questions I will answer is, I will refer you to what page number in your notes. Just like just now we tried to do that problem, the answer's right there on page 5, and you can't get it. Well, why is that? The answer is staring you in the face. I need to move on. If you do your homework, if you do your tests, I will not tell you whether or not it is right or wrong. Nobody does that. You will be able to tell whether it's right or wrong, because then what I'm asking you to plot, the output voltage and the theoretical output voltage, they got to look alike. They got to lie on top of each other, or if not very close to each other. Then you will know you did something wrong. Then you go back and you try to figure out, what did I do wrong? I'm not going to be on your job to tell you what you're doing wrong. What circuit is this? What circuit is that?
Inverting op amp.
Oh, Lord, my God.
That's the differentiator, the one we doing for homework.
This is a differentiator. With the switch, it was the integrator. With this, if C was here and R was here, that was the integrator.
Yes, sir.
Now let's prove that. What's IN equal to? What's IN equal to?
That would be the current through the capacitor.
And what is that equal to?
VC divided by RC.
Young man, for God's sake.
C to VDT.
Thank you very much. C, which V?
The input,
Which-
the input voltage.
Why is it the input voltage? Because then you're telling me the input voltage is cross capacitor. How do you know the input voltage is cross capacitor?
The voltage across just the negative and the positive. The VD
Zero.
VD is 0. VD is 0.
So that means no current going through and going up towards the resistor.
No, that's another thing. There's no current going this way. That tells you I out. I out equals I in. What's I out equal to? What's I out equal to?
That's the voltage across the resistor divided by the resistance.
All right, so let's call that VR. That's VR divided by R. What's VR equal to?
You can use KVL again.